Hello. Today we're going to present a method that we derived for geolocating crash data throughout Boulder County, of which the data was provided to us by the Colorado Department of Transportation. My name is Dave Watson, and I am the GIS manager for the Public Works Department in Boulder County. Mac Johnson has been a GIS intern in our office for over a year and has performed most of the work on mapping these crashes. He will tell you a little bit about himself, but I want to say that he has done a great job at synthesizing, organizing, and geolocating this complex, multifaceted data. Plus, he has developed methodology that will help us maintain this vital data set for years to come. Let me also give a shout out to another GIS professional on our team, Manuel Larson Santos. He built in some Python scripting as part of the process to incorporate some efficiencies and mass process large quantities of data. Now I will turn it over to Mac Johnson.
Thank you, Dave. A little more about myself. I grew up in Colorado and graduated from CU Boulder with a degree in GIS and environmental studies. In my free time, I like to go camping, dirt biking, rock hounding, all that outdoorsy stuff. But anyway, let's dive right in and allow me to show you our interesting process for mapping crash data. After an extensive analysis and identifying different types of location information, a multi-step process was created to map all of Boulder County's crash data. Based on how the data was grouped, individual geolocating methods were derived. We were able to achieve this by using CDOT's latitude and longitude information, geolocating with an address locator, and linear referencing. Shown here on this graph are the different methods and corresponding percentages in which the crashes were mapped, the majority being CDOT's on-system crashes with latitude and longitude data already provided, followed by crashes mapped using a linear referencing system, and then crashes geocoded at an intersection. Considering all crashes since 1986, we were able to map about 50% of those records. Records in the 20th century had very little location information, proving difficult to map. As time progressed, so did the crash reporting, methodology, and location accuracy. The majority of crash records that were mapped fall between 1999 and 2018, with more than 90% of crashes mapped in recent years. The 49% shown here was displayed on the map in the previous slide, which we will show again at the end of this presentation. The records labeled as not mapped have little to no location information, while the category called potentially has location information, but with only CDOT roadway abbreviations or mile marker numbers. The category called other error refers to all records that could be mapped but have strange nomenclature with their location information and would require further investigation. Most of these errors refer to the distance a crash occurs in relation to two intersecting roads. Some of these values include 99,999 feet west, 50 miles north, X, or just a north, south, east, west abbreviation. So some of the importance of crash data. The crash locations are important to end users who want to make decisions to reduce crashes. In our case, end users are our traffic engineering team and multimodal group. However, we'll be publishing this data for public use. Specifically, the multimodal group is actively engaged in the Vision Zero initiative, and this crash data will help them pursue the goal of zero crash deaths and severe injuries. Some of the data prevents us from geolocating and geoprocessing, creating some unexpected variances. Years ago, we had to map crashes manually from paper reports. One of our colleagues, Tom, used to commute to a CDOT field office, manually search for Boulder County crash records, photocopy them, and then manually add each one to an internal database. We've come a long way by automating the process with data from CDOT.
In order to understand the data more clearly, we needed to determine the flow of information from the moment of each crash through to the point when we received the data. Even though we are mapping all crashes throughout the county, including the municipalities, this flowchart pertains to unincorporated Boulder County specifically. Other jurisdictions may have slightly different processes. At each crash, the Colorado State Patrol shows up on site, investigates, and prepares the report. From time to time, CSP is on accident alert due to the high number of crashes in the region, and they may not have the resources to show up at each site. In that case, those involved in the crash can go online and submit a report themselves. Note, individuals should only do that if they know that the CSP is on accident alert or when 911 dispatch informs them that it's okay. Otherwise, the person may be charged with leaving the scene of an accident. The CSP reports the crash to the Colorado Department of Revenue. The DOR updates individual drivers' records and then removes all personally identifying information. The data is then acquired by CDOT. I want to give a special thank you to Elisa Babler, Paul Clayton, and Boyan Quinn for working with us in providing, explaining, and contextualizing the data. Elisa and her team put in a lot of work to clean the data from DOR, geolocate crashes on CDOT roads, what they call on-system crashes, and prepare the information in their database for a gazillion reports, analyses, and data distribution. This process would not be possible without them. CDOT provides us with every crash reported in Boulder County, including CDOT roads and municipalities. They also provide all crashes along our county boundary shared roads, where the crash may be reported in the neighboring county. The rest of this presentation speaks to the methods we developed for mapping off-system crashes, those crashes that occurred on non-CDOT roads. Our plan is to provide those mapped crashes back to CDOT in the form of a live updated feature service with lat-long fields built into it.
All right, here is a snapshot of the investigating officer's crash reporting manual, where the location information is recorded. As you can see, there are several different sections where information can be recorded, which include latitude and longitude, highway number and mile point, name of intersecting roadways, and distance from an intersection. Ideally, accurate latitude and longitude data is preferred. However, that is not always possible. So other ways of capturing location data are provided. The location data that gets written into these forms eventually comes to us as a spreadsheet looking like this graphic below, with the on-road/street showing up as LOC1 and the reference intersecting road/street as LOC2. The link field is a combination of the other boxes to the right in the first graphic, such as intersection offset, miles, feet, and direction. Some of the data processing steps. To increase the successful match rate of our geocoding steps, we found it was important to go through the crash records and make spelling changes to the location fields, as mentioned in the previous slide. We wanted to leave the data as intact as possible, and therefore changes were minimal. A good example of this is South Boulder Road, where it can have several ways of being spelled. Manuel helped us here by building a frequent alternate name dictionary in Python, which over time detects common variations in road name spellings, then changes those spellings to fit our geocoding process. First step is the coordinate XY method. When requesting the data from CDOT, they explain that all crashes occurring on their road network have the latitude and longitude information verified and corrected before they send it to us. This makes mapping these crashes straightforward. We begin by grouping the records on the road with the roadway type as state highway, and then using the add XY data tool, bring them into the map. Again, we must give CDOT a lot of credit, for this is an extremely time-consuming and tedious process to ensure the data they send us is accurate. Next step, geocoding method. We created our own address locator tool using a centerline layer that is provided by our emergency responders. We chose that layer because it has been specifically designed for geocoding and it is comprehensive throughout Boulder County. All the records in this group have their location fields cleaned and corrected before they can be run through this tool. The output gives each record a matched, tied, or unmatched value. From here, we manually go through the tied records and assign the correct location. Unmatched records are looked through in the same way, but crashes that cannot be accurately mapped are combined into another group to be dealt with at a later time. We were able to achieve an 89% match rate for this geocoding process after using the frequent alternate name tool. And so a quick summary of linear referencing. Using the built-in linear referencing tools in ArcGIS, it is required to have a center line with measured values and an event table. CDOT provided us with the centerline feature class and created the event table described on this slide. At a minimum, an event table requires a route ID and an event value, which is the distance along the measured route. The first step for this process is to geocode the record to its corresponding intersection, using the emergency responders layer based on the information found in the location fields. For instance, a record with location information as Arapahoe Road, 528 feet east of North 75th Street, would be geocoded to the intersection of Arapahoe Road and North 75th Street. From there, the distance values are converted to miles so that the CDOT linear referencing layer can be used. The route ID is a unique numbering system created by CDOT, and the event value is the value that is used to move a point along a measured line segment. Crash ID is a unique value that we in Boulder County Public Works created for every record as soon as we receive the data from CDOT. In fact, we have a unique ID for every record in Public Works. This ensures that each record is tracked accurately throughout the entire process. Next, the Locate Features Along Route tool is used, which identifies the position of the crash along the CDOT linear referencing layer line segment. This provides the exact measured distance of where the point sits on the segment at the intersection, as well as a route ID. From there, the records are split into groups based on direction, so north, south, east, and west. The converted link value is then joined with the segment value to create the event value. For all records that are north and east, the value is added, while records that are south and west, it is subtracted. These values can then be used to create an event table, which contains the unique crash ID, route ID, and event value. This table can be used with the Make Route Event Layer tool to map the crashes. For some of the records, multiple points resulted in more than one direction. To reduce this back to the accurate point, Manuel helped build a Python script that would search through the duplicate points and based on their direction value, identify the correct one. For example, if the direction value is east, then it looked for the point with the highest X value. And if the point is south, it looked for the lowest Y value. We decided to utilize a linear referencing centerline feature class from CDOT so that the LRS and the crash data were from the same source. Here's a simple example of how crashes were mapped using the linear referencing system, as I described earlier. First, we set the tolerance of a crash occurring at an intersection to be 30 feet or less when looking at records with distance values in the link field. Broadly, in Boulder County, road right-of-way is 60 feet. So half the distance is 30 feet, and we decided that any crash with a distance of 30 feet from the intersection, 30 feet or less from the intersection, is at the intersection. For records that have a distance value greater than 30 feet, They are moved from the center of their related intersection based on distance and direction shown here. By having the measured segments of the CDOT linear referencing layer, we can accurately place crashes any distance from an intersection. For records that have an ordinal direction, such as northeast, northwest, southeast, and southwest, our linear referencing process is the same as with the cardinal directions. Although, when we ran into the duplicate record issue mentioned before, our process changed slightly. First, we placed 4 points outside the 4 corners of the state of Colorado. Then, using the near function in ArcGIS, we found the point closest to the corresponding Colorado state corner based on that record's ordinal direction. It really does help when you live in a rectangular state. Due to the variability in the data and different geolocation methods, there are known but small variances with an acceptable tolerance. The tolerance is within the precision required by end users, like our traffic engineers and multimodal professionals. They only require precision in relation to other features such as turn lanes, proximity to intersections, safe distance for cyclists, etc., etc. As a result, we have a crashes feature class with corresponding feature service ready for use today. Thank you for your time, and we are now happy to answer any questions.